So we're continuing with chapter 6. We're talking about waves, and now we will continue. So just announcements wise, chapter 5 homework is due on the 8th. Chapter 5 quiz will be on the 8th. The chapter 6 homework will be due on the 15th, and the chapter 6 quiz will be on the 15th. So when we look at a wave, if we describe a wave has a wavelength, a velocity, an amplitude. It also has a frequency, which is the number of waves that pass by in a second, and a period, which is the time it takes for one wave to pass by. Frequency is the number of cycles that occur during a given time. We describe frequency with the unit of hertz, which is 1 cycle per second. Period is the time it takes for a wave to travel a distance of one wavelength. And frequency and period are inversely proportional. So frequency equals 1 over period. So if a wave has a frequency of 4 hertz, 4 full wavelengths will pass in a second. And the period is the seconds per cycle. So if 4 full wavelengths pass in a second, that means the period is 1/4 of a second. So here is a comparison of 2 waves at different frequencies that travel at the same velocity. So here we have one at 4 hertz. You get 4 cycles in a second. One at 8 hertz, you get 8 cycles in a second. So this has, if you double the frequency, you have the period, and you have the wavelength. So the speed of a wave is the wavelength over the period. And that means that the speed of a wave equals wavelength times frequency. So the speed of a wave in meters per second is its wavelength times in meters times its frequency in hertz. This also means that frequency is speed over wavelength, and wavelength is speed over frequency. It allows you to go between frequency and wavelength if you know the speed. Now, electromagnetic waves consist of vibrating electric and magnetic fields that will oscillate perpendicular to each other and perpendicular to the direction of wave propagation. The field energy will radiate outwards as fast as it can go, which is the speed of light. And the speed of all electromagnetic waves in a vacuum is the speed of light. So c, the speed of light, is 3 times 10 to the 8th meters per second. And the speed of light in air is a little bit slower, but to 3 significant figures, it is the same. You'd need more digits. So to a good approximation, this is also the speed of light in air. So if you have an electromagnetic wave that consists of electric and magnetic field vectors, the electric field vector, if the electric field vector is going up and down, and the magnetic field vector was going right and left, the direction of propagation will be out of the board. So they're all perpendicular to each other. So this is an example. As the electric field varies, it creates a magnetic field. As the magnetic field varies, it creates an electric field, and the whole thing propagates. Then what? Okay. And there's a huge range of electromagnetic waves. They vary based on their frequency or their wavelength. And the human eye only detects a very small portion of them. This is what we call visible light. This is with wavelengths between 400 nanometers and 700 nanometers. Name? That is what our eyes can detect. Now, this is basically the center of the light that comes from the sun, so it sort of makes sense. But that is our eyes. There are things that can detect beyond the range that human eyes can detect, into the infrared and into the ultraviolet. Yeah, this is light. So here is a short video about the electromagnetic spectrum.
Hey, it's Professor Dave. Let's learn about light.
He knows a lot about the science stuff. Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So here, let's calculate what the wavelength of the radio waves, because radio waves are electromagnetic waves. They're just light, same as everything else, produced by a station with an assigned frequency of 600 kilohertz. So our first step is to convert kilohertz to hertz. 600 kilohertz is 600 600,000 hertz, or 600 times 10 to the third hertz. So that's 6 times 10 to the 5 hertz. And since the speed of light is c, we can set c equal to wavelength times frequency and solve for wavelength. The wavelength equals c over frequency. So 3 times 10 to the 8th meters per second divided by 6 times 10 to the 5 hertz gives us, well, 3 divided by 6 is 0.5, and 10 to the 8 divided by 10 to the 5 is 10 to the third. So 0.5 times 10 to the third meters, or 500 meters. So radio wavelengths for AM and FM differ because the frequencies differ. AM is in the kilohertz, hundreds of kilohertz range. So AM is centered around, the low end of AM is around 80. AM is around 800 kilohertz, 8 times 10 to the 5th hertz. So it will have, something, a wavelength on the order of 300 to 400 meters, while FM is around 90 megahertz, which is 9 times 10 to the 7 hertz. So it has a wavelength of around 3.5 meters. So because wavelength is speed of light over frequency, as the frequency gets bigger, the wavelength gets smaller. AM wavelengths are longer than FM wavelengths by about a factor of 100. Because they differ in frequency by about a factor of 100. So let's do an example. Our local public radio station, WBEZ, broadcasts at a frequency of 91.5 megahertz. So what is the wavelength of the WBEZ radio? So the speed of light is 3 times 10 to the 8th meters. The exact value is this, 299,792,458 meters per second. But 3 times 10 to the 8th meters per second is a good approximation. So WBEZ broadcasts at 91.5 megahertz. So what's the wavelength of the WBEZ radio wave? I'll let you work on that for a minute or so. Remember, megahertz, mega is million, so 10 to the 6th. Quick reminder for light. Yep. So speed of light is frequency times wavelength. The wavelength is the speed of light divided by the frequency, so 3 times 10 to the 8th meters per second, divided by 91.5 megahertz. So that's 3 times 10 to the 8th divided by 91.5 times 10 to the 6th, which comes out to 3.28 meters. Now, visible light has frequencies in the range of around 10 to the 14 hertz. Therefore, visible light has relatively short wavelengths. If you had light at 10 to the 14 hertz, you would get, because we're dealing with something like 10 to the 8th divided by 10 to the 14, 10 to the minus 6 meters. So visible light wavelengths, it turned out, are all a little bit less than a millionth of a meter. They're in the hundreds of nanometers range. Visible light actually ranges from around 400 nanometers to around 700 nanometers. We generally express the wavelengths in nanometers because 1 nanometer is 10 to the minus 9, so we don't use negative exponents. But visible light range extends from 400 to 700 nanometers, or 4 times 10 to the minus 7 to 7 times 10 to the minus 7 meters. And the human eye perceives these different wavelengths within the visible range as different colors because we have different cells in our eyes that are sensitive to different ranges of wavelengths. And by comparing the strength that these get excited, we can get, that's how our brain puts colors together. So the brightness that we see depends on the energy of the wave. And the reason there are primary colors has to do with biology. Because we have 3 different color sensing cells in our eyes. So if we were different species, we might have more primary colors. We had 4 different sensors in our eyes, or if we were like dogs and only had 2. So a red LED will emit light with a wavelength of 660 nanometers. What is the frequency of this light? And that 660 nanometers is an actual wavelength for red LEDs. I got it from some product source. Don't remember where I looked it up, but I found an actual LED on the market that had that wavelength. So I'll give you guys a minute or so to work this out. Remember that a nanometer is 10 to the minus 9 meters. Yeah. So speed of light is equal to frequency times wavelength. The frequency is just going to be speed of light divided by wavelength. So 3 times 10 to the 8th meters per second divided by 660 nanometers is 3 times 10 to the 8th divided by 660 times 10 to the minus 9. And that comes out to 4.55 times 10 to the 14 hertz. Rounded to 3 significant figures. So visible light will always be in the something times 10 to the 14 hertz range. This is the low end. The high end is well, the high end is going to be 7.5. So sound waves are not, they're compressional waves. They're longitudinal waves that travel through matter. So they're like pressure waves traveling through matter. So, for example, the vibration of a tuning fork will produce a series of compressions. When it moves forward, it compresses the air in front of it. When it moves backwards, it rarefies, it stretches out the air. So compressions, high pressure regions, and rarefications, low pressure regions. And with continual vibration, a series of high and low pressure regions will travel outward and they form a longitudinal sound wave. And then this vibrates your eardrum and you detect that. So you have compressions and rarefications. They reach your ear, which has a membrane that can be moved back and forth by the compressions and rarefications. And that's what you hear. So as the end of the fork moves outward, it compresses the air. When it moves back, it produces an area of low pressure. So here's an example of a longitude, a sound wave. You can see there's more higher pressure air here, and then there's lower pressure air in between. And that's what you're listening to right now. It's moving a lot faster than this. The frequency is a lot higher than this, but that is an illustration of what you've done. And similar to electromagnetic radiation, sound waves also have different frequencies and form a spectrum. We divide that spectrum into fewer pieces. We're less interested in different varieties of it because it covers, for practical purposes, it's actually a smaller range and they have fewer different regions that we actually use. So basically we divide sound into sounds below what we can hear, which are infrasonic. Though sometimes you can feel them as just vibrations. Audible sounds, so human hearing ranges from around 20 hertz to around 20 kilohertz. Though that upper end is not as high as you get older. Or if you're like me and have not treated your ears as well as you should have. And then above that, there's ultrasonic. And there's actually an upper limit to how high in frequency you can make a sound wave go, because you start hitting issues with like air not transmitting right. So the upper limit is around a gigahertz. Where stuff starts to fail. So the audible region for humans, we can hear between around, at the very low end, 20 hertz up to around 20 kilohertz. And this is, we can hear sound through the vibrations of our eardrums caused by the sound waves propagating disturbance. So what happens is that pressure wave reaches your eardrum, it moves your eardrum, it gets transmitted through a series of tiny, tiny bones into your inner ear. And in the inner ear, it vibrates some hairs, depending on what frequencies it vibrate, what hairs it vibrate, depends on the wavelength or frequency. and that is how you detect sound. And here is a sweep covering the audible region of human hearing. Though, to be honest, I'm pretty sure a combination of YouTube compression and the speakers we have are killing some of the higher frequencies. I'm not 100% sure there, but I wouldn't be surprised if that was the case. Because this seems to only get visible lower than I would, audible at a lower frequency than I would expect. But then also, I've probably done unfortunate things to my hearing. Let's try this again. Just want to make sure everything is there. Yeah, so I think the bottom got cut off because of the speakers here, but so this is my loudest. And then this is cutting off at the limit. So loudness or intensity is a relative. Loudness is a relative term. You can really only say that this thing is louder than this other thing. You can't, not define. If you want a quantitative term, you can use intensity. It's a measure of the rate of energy transfer through a given area. And intensity can be measured in, how much power per unit area is delivered. So we measure intensity in watts per square meter. And the human threshold of hearing is at about 10 to the minus 12 watts per square meter. And an intensity of about 1 watt per square meter is physically painful. Like it hurts. And intensity decreases with distance from the source. So if you double your distance from the source, your intensity will as an inverse square law. So if you double the distance you are from the source, the intensity will decrease by a factor of 4, assuming you're in an open area and the sound can spread all over. And that, many things are inverse square laws, like gravity and intensity and other things, because as you spread out, this thing gets spread out over effectively the surface area of the sphere, and the surface area of the sphere is proportional to its radius squared. So the reason it's an inverse square law is because we live in a 3-dimensional universe. Now, the common way that we measure sound intensity is with the decibel, which is a bizarre unit, which has a long and strange history. But for sound, we could use it as a measurement of sound intensity. Technically, it's a measure of, it's like a comparative ratio between some reference and another signal. It was invented by the telephone company and then named after Alexander Graham Bell. So it was originally invented for like electronic signals and stuff, but the reference signal for sound is the bottom of human hearing. So the bell is unit of intensity. It's named in honor of Alexander Graham Bell because it was, invented by the company he founded. And the decibel scale is not a linear scale. It's a logarithmic scale. So every bell, of which a decibel is a tenth of a bell, so every 10 decibels, every time you increase by 10 decibels, you multiply the intensity in watts per square meter by a factor of 10. So every time you go up by 1 bell, you go up by a factor of 10 because it's a logarithmic scale. So When the sound intensity is doubled, the decibel level increases by 3. Now, 0 decibels is the threshold of hearing. 10 to the minus 12 watts per square meter. That's how it's defined for sound. And then as you go higher, you can get more powerful. So a rustling leaf is about 10 decibels. A quiet room is around 20. A soft whisper is around 30. Quiet library is around 40. An average home around 50. Conversational speech is usually around 60. City traffic is around 70. Average factor is maybe 80. The subway train is around 90, and exposure to sound of over 90 decibels for long periods can affect your hearing. A boiler shop is around 100. A rock band with amplifiers can be around 110. A riveting machine is 120, and sound levels above 120 can cause pain. A jet plane's takeoff is around 140, and a rocket launch is at 180. So here, if a riveting machine has an intensity of 120 decibels, while a factory has an intensity of 80 decibels, how many times more intense is the sound of a riveting machine than the factory? So here, remember that every 10 decibels is a factor of multiplying by 10. So first, we figure out the difference between them. That's 40 decibels. Adding 10 decibels multiplies the intensity by a factor of 10. So 40 decibels does that 4 times, so 10 to the 4th times the intensity, or 10,000 times. So a riveting machine puts out waves that are 10,000 times more intense than a factor, average factor. So basically, every time you add 10, you add a 0. So if I have a pair of earplugs that will reduce intensity by a factor of 100, so they cut down the power passing through them by a factor of 100, what intensity would I hear a 98 decibel rock concert? So here, plus 10 decibels is 10 times the intensity. So minus 10 decibels is 1/10 the intensity. I am cutting it down by a factor of 100. So that's minus 20 decibels. So 98 decibels minus 20 decibels will be 78. So, no, that's why if you have earplugs, they're probably rated in decibels. And that's why, like an equalizer will tell you how much plus or minus decibels you're changing various frequencies. The other thing is that our hearing is not equally sensitive to all frequencies. It's most sensitive around a few thousand hertz. And then it peters off at both ends. Now, sound waves with frequencies greater than 20,000 hertz cannot be detected by the human ear. though they can be detected by some animals. So, you know, a dog whistle, that silent dog whistle, that's just because it's at a frequency that's above human hearing that dogs can hear. And bats primarily use ultrasonic sound to navigate. So you can reflect ultrasonic sound off of objects. And reflections of ultrasonic frequencies can be used to examine parts of the body, like an unborn child, or your heart, your kidneys, or whatever, which is much less risky than using X-rays, particularly for an unborn child, because ultrasound is just sound, just vibrations, while X-rays are at an energy level where they can affect cells and DNA cells. So you don't necessarily want to put that on a developing fetus, which is very delicate. Also, ultrasound is very useful for cleaning small, hard to reach recesses, particularly in things like jewelry or lab equipment. You get an ultrasonic cleaner where it sends ultrasound through a water bath or a liquid bath to basically vibrate the dirt off things. And the other advantage of ultrasound for imaging is that because of its high frequency, it has a short wavelength. This is particularly important for imaging inside the body. You know, if you used audible sound, the wavelength would just be too long. Because the speed of sound is also higher inside the human body than it is in air. Generally, the speed of sound is faster the denser the material is. So, like, it's very fast in something like metal. But if you want good resolution, you want to have small wavelengths. That's just a general thing, that the resolution of what you can image with a wave is proportional to its wavelength. So shorter wavelengths give you more detail. So here's a video about how ultrasound works for medical imaging.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
And yeah, it's basically harmless, mildly uncomfortable, because they slather you with goop that is very cold. The purpose of that is to make sure that there aren't any reflections in the transition between caused by stuff in between the transducer and your body, so that the goop transmits sound about the same as your body. So you can stick the transducer in the goop and it's directly interacting with stuff that transmits sound about the same as your body, so it doesn't reflect off the air or something. And then sometimes they push hard, but that's about it. But yeah, and so the same thing is used by bats and dolphins and other cetaceans to image their environment. So bats use reflection of ultrasound for navigation and to locate food. Dolphins and other whales use reflection of ultrasound to locate things in the water. And there are more advanced forms of ultrasound that can be done as well, where you can do more, we just covered basic ultrasound imaging, but you can actually get more information with something functional ultrasound. So functional ultrasound can extract information about more than just like basic density and doesn't reflect things. There's two different types.
In addition to showing anatomic structures, functional ultrasound shows color image maps that can indicate the softness or hardness of specific tissues, movement and velocity of tissue or blood, and other physical characteristics. One type of functional ultrasound is Doppler ultrasound. If you've ever listened to how a siren sounds as it approaches, passes, and drives away, you are hearing what's called the Doppler effect. The waveform is compressed as the ambulance approaches, making it sound higher pitched, and it's stretched as the ambulance departs, making it sound lower. Doppler ultrasound uses the same principle to determine the speed and direction of the blood inside your arteries. The transducer is held at an angle to the blood vessel, and the altered frequency of the echo returning to the transducer from the blood flow tells the computer the blood's speed and direction. This information is displayed in different colors on the final image to show changes in or absence of blood flow, indicating blocked or narrowing blood vessels, decreased circulation, heart valve defects, blood clots, bulging arteries, or even the presence of new blood vessels and flow in tumors. Another form of functional ultrasound, elastography, can be used to differentiate tumors from healthy tissue based on the tissue's relative stiffness. Healthy tissue and benign tumors tend to be compressible, unlike malignant tumors, which are more firm. This compression was originally done manually, but newer elastography systems send out high-pressure pulses that compress target tissues by a predefined amount of force and display the resulting compression levels in various coded colors.
And the Doppler effect is used for all kinds of things. You may have heard of Doppler radar, which is using the Doppler effect to study the movement of weather systems by reflecting radar off of them. And it's also how radar guns work to determine the speed of a car. The speed of sound depends on the makeup of the particular medium that it's passing through. The speed of sound in air is around 344 meters per second at room temperature. That's around 770 miles per hour. That's at 20 degrees Celsius. And the speed of sound will increase with increasing temperature. So at 0 degrees Celsius, it's around 331 meters per second. So the warmer it is, the faster the speed of sound is. And in general, the speed of sound increases as the density of the medium increases. So the speed of sound in water is around 4 times that of air. And that's similar to the speed of sound in your body, because your body is mostly water. And the speed of light is way faster than the speed of sound. So in many cases, we hear something, we see something well before we hear it. And in fact, because the speed of light is so fast, if we can hear it and see it, the difference between the time we see it and the time we hear it can be easily used to calculate how far away it is. Because the speed of light is practically instant. So you can just use the speed of sound to work out how long it would start to see you. So for example, a 5-second lapse between seeing lightning and hearing the thunder indicates that the lightning occurred at a distance of about 1 mile away. So if you see something and it takes 5 seconds for the sound of that something to reach you, that happened about a mile away, because the speed of sound is about a fifth of a mile per hour, or about a third of a kilometer per hour. So let's work out the wavelength of a sound wave in air that has a frequency of 22 megahertz. So this is an ultrasound wave. So given that the speed of sound is 344 meters per second, and the frequency is 22 megahertz, if we convert this to hertz, that's 22 times 10 to the 6 hertz. The velocity of sound equals the wavelength times the frequency. So the wavelength is velocity divided by frequency. So 344 meters per second divided by 22 times 10 to the 6 hertz gives us 16 times 10 to the minus 6 meters, or 16 micrometers. And that short wavelength is why ultrasound is good for imaging, because it can see detail that is like that small. Well, in your body, it's going to be maybe 4 times larger than that as a wavelength, but that's the scale that we're talking about. It's on the scale of micrometers. So we can see little things. So if the speed of sound is 344 meters per second, what is the wavelength of a high C at 1046.5 hertz? That's the ISO definition of a high C. So because tuning is standardized. So velocity is frequency times wavelength. Wavelength is going to be velocity divided by frequency. So that'll be 344 meters per second divided by 1046.5 hertz, or 0.329 meters, or 32.9 centimeters. And it turns out that if you made a high C in like a flute or some other woodwind instrument, it would need to be about a quarter of this length, because of how they work. You know what? I think that'll be it for today. So have a nice day. I'll see you next week. Enjoy your day off for Easter. Yeah. See you next week. That was fun.